Okay, so at this point, this is the third session on our schedule of, I think we have 6 sessions before we get together in person. And to this point, we're meeting here on May 26th, and we should be through chapter 5. That's the ideal. So if you're not through, and I know Joe, you're here, but those people watching it on the video, hopefully they're also keeping up with us. And one area that I wanted to make sure everybody understands, I'll go over it pretty quickly, but I'm going to share the whiteboard here. And so hopefully, do you see the whiteboard there?
Yes, yes, I do.
Um, Now if I can get my cursor over there. All right, there we are. Ah, every time I put the cursor, the thing on it, it's on the wrong page. All right, how do I get that over there? If I move the all right, it wants me to use see what happens here if I use the mouse instead of the pen. This is the IV curve. This is what happens when I try and write with a mouse. Let's see if it's gonna. All right. Boy, that's weird. I'm gonna move this screen over into the other screen and see if that helps. Yep, that'll help. All right, it just wants me to use this screen. All right, so the IV curve for a solar panel is going to look something like that. And we call it the IV curve because that's amps and volts.
Mhm.
This is the zero axis. And this particular, when amps equals watts equals amps times volts. So that's the power equation. That's the first equation that you really need to have memorized. It's not that hard, but it's really just a relationship between amps and volts, and that's when you get watts. So if you were to plot this on a curve of a typical solar panel, it would look something like that. And the theoretical maximum amps is referred to as the ISC. So the amps short circuit. And the reason why I always say the theoretical maximum amps is at ISC, there's 0 watts, right? Because anything times zero is going to equal zero. And you can't measure amps unless something's flowing. So you're never able to measure ISC. It's just a theoretical number. As soon as you get even slightly off of that zero axis, then you can begin to measure it. But technically, ISC you can't measure. And VOC is the actual maximum volts. So if you were to stick a multimeter onto a solar panel when it's not hooked up to anything, you're measuring VOC. So these are the two theoretical maximum numbers, the theoretical maximum amperage and the maximum voltage that panel can produce under standard test conditions. So standard test conditions are going to be 1,000 watts per square meter, um, 25 degrees Celsius, and 1.5 atmospheres. So how did they come up with that? Well, a group of, middle-aged white guys who met in Paris just said, we need a number. How about today? Right? So they go outside and they go, all right, we're at sea level, about 1,000 watts per square meter. It's about 77 degrees, which is 25 degrees Celsius. And in Northern Europe, North America, the sun passes through about 1.5 atmospheres. We don't really care about the atmospheres. It's just there. We're more worried about what is the irradiance, which is the 1,000 watts per square meter, and what is the temperature. And temperature affects voltage. Irradiance primarily affects amperage. They both affect both, but it's really skewed. So if clouds come over, it'll drop the amps. If it gets colder, it'll increase the voltage. It'll also increase the amps a little bit, but not dramatically. So So those are the measurements we're worried about. So when we design our systems, we want to use the theoretical maximum amps in designing our wire sizes, and we want to use the maximum voltage in designing our strings so we don't exceed the maximum voltage allowed by law and or the voltage of the equipment. Now, somewhere along this curve, the panel will produce the maximum amount of power. So that's going to be somewhere in this elbow here. And that's known as the Pmax or the maximum power point, MPP. They haven't really standardized on these acronyms. So you'll see them referred to differently in different places. But that is the maximum power point. And there is a voltage associated with that. And there is an amperage associated with that. So the amperage is the IMP, the amps at the maximum power point, and the voltage is the VMP, which is the volts at the maximum power point. Sometimes you'll see these things as Vmax, VMP, Imax, IMP. Again, just referencing the same thing. Now, what's confusing to a lot of folks is Vmax, you would think would be the maximum voltage, but it's not. It's the voltage when it's at the maximum power point. The VOC is the maximum voltage. So it's easy to get those terms confused in your head. So these are truly the operating voltages and the operating amperages when our system is behaving properly. So we have the theoretical maximums, and then we have the actual operating. And the reason why it's going to be operating at the maximum power point is there's a device called the MPPT, which is the maximum power point tracking device, and it's located in the first piece of electronics that is connected to the solar panels. That could be an optimizer, it could be a microinverter, it could be a charge controller, it could be a string inverter. Whatever the first piece of electronics is, that's where that MPPT is going to be located. And what that does is constantly adjusts where it moves the output to the maximum power point on a millisecond by millisecond basis as conditions change. So if suddenly you have clouds that come out and your curve jumps to something like that, then all of a sudden the maximum power point jumps down to here. If it gets warmer, it's going to jump out there. If it gets colder, whatever. So this maximum power point's always shifting around, but it is controlled by the MPPT, by the first piece of electronics that is connected to that panel. So one of the reasons why, if I've got a series of solar panels and they're all connected, let's say I've got these 4 panels and they're connected in a string, and I've got another string of 4 panels. You wouldn't configure it this way, but just for illustration purposes, we're going, and a string is going to be positive to negative and so on. So the voltage increases, the amps remain the same. And let's say we go into a combiner box. So you're going to jump over here and that's going to connect in, and you're going to jump in from over here and that's going to connect in, and they're going to go into bus bar. And let's say we leave with only 1 string. Okay, so that's a combiner box where you're taking multiple strings and combining them in parallel in the box. And then it comes in and it goes to, well, first it goes to a DC disconnect. And the DC disconnect is now in this world generally connected to an inverter. So this would be a string inverter system. All right, now where is the MPPT in all of this? Well, this string is going to go through that DC disconnect and it's going to connect into that MPPT. So by combining these 2 strings, there's only 1 MPPT. So all of the array is going to act as a single unit. it's being controlled by one MPPT. So if this panel suddenly gets shaded, well, that's going to affect all 8 of these panels because it's going to draw down and it all is going to behave as if it were just one panel. So that's the downside of having a string inverter in a combiner box, is if one panel is affected, it affects all of the panels in the array. So that's one reason why we've started the more common practice is if you had 8 panels, more often you're going to have optimizers or microinverters, and those are going to be attached to each individual panel. So there's going to be an electronic device here, an electronic device there. So every single panel is going to have its own electronic device, and every single panel is going to have its own MPPT. So if this panel gets shaded, well, it affects that panel, but it doesn't affect any of the other 7 panels. So you maximize your output. Well, the reason we used to do the combiner boxes was just to save wire. You know, you're saving on some wire. But the power output is more valuable than the wire. So we tend to now not use combiner boxes. We'll oftentimes use junction boxes. So let's say we have this box and we still have a string inverter with a DC disconnect. Oftentimes you'll have the strings coming in, a string coming in here. Rather than combine them and only leave with one circuit, more often than not now we'll come in with both strings and we'll go into the inverter, and the inverter will have 2 MPPTs. So now this string behaves as a unit and that string behaves as a unit. So if this is shaded, it only affects half of the array, not the whole array. So we're not saving a little bit of wire here, but we are getting better output. So you'll oftentimes see string inverters, they might have as many as 4 MPPT ports. So every single string can come in into that inverter. But more often than not, if it's on a rooftop, these electronic devices on the rooftop have to be installed anyway because of rapid shutdown. So let me explain what rapid shutdown is. What rapid shutdown seeks to fix is, let's say we've got a roof here on a house, and we've got our solar array up here. And the way we used to design these systems is you'd probably put your combiner box or your junction box underneath the array, and then you drill a hole into the attic, and maybe you put the wire on the underside of the rafters or whatever, possibly pop out of the building over here, come down to a DC disconnect. The meter, the electric meter might be right here. Then this goes back into the building, goes into the basement, and in the basement, we now have an inverter, and the inverter connects back out and goes to an AC disconnect, which is required to be out next to the meter within 10 feet. And then it would go back into the building and it would go to the service panel. So here's the main, which is connected to the meter, and we'd hook in here. Well, you can see it's pretty inefficient, for one thing, a little bit cumbersome. You're drilling a lot of holes in the building and all of that. But the other issue is, let's say your house suddenly catches on fire. It's the middle of the day, and the first responders come and they want to put out the fire. Well, the first thing they do is they go to the meter and they'll pull the meter. So the meter acts like a fuse, and it simply disconnects you from the grid because they don't want any power to be out there, to be in the building, because they're going to be whacking holes in the walls. They're going to be cutting holes in the ceiling. They don't want to get electrocuted. So they're disconnecting you from the grid. Now, on your meter is a little label that says, warning, there's a second power source here. So that's required. And they look around within 10 feet. Oh, here's the AC disconnect. And it says solar array disconnect. So you disconnect, you turn that off. What did it just do? It turned off the power at the inverter. So now it's no longer generating power from the inverter. But if the sun is shining, these wires going all the way down, they might have turned off the DC disconnect if they thought about it. But if they didn't, these wires all the way to the inverter are still live. And they could be live with as much as 600 volts in a residential setting. So the fireman climbs up onto the roof and he takes out a chainsaw and he starts cutting through the roof to vent the fire, to vent all the smoke out of the building. And he cuts through a 600-volt electric line and it kills him. So that's what they want to avoid. So in 2014, they passed what was known as the rapid shutdown provision that basically says, when I turn off this switch here, I want the power to disconnect up here at the array. I don't want it disconnecting at the inverter. I want it shutting off at the array. And in 2014, the industry sort of looked at them and go, how do we do that? And the National Electrical Code said, not our problem. Do it, because we're all about safety. So if you don't do it, go out of business. That was basically their attitude. So what somebody came up with initially was, well, tell you what, instead of putting the inverter here, let's put it right up next to the array. Well, on a regular residential house, that's not going to work because you've got this 100-pound piece of equipment sticking up there. But on top of Walmart or on a flat roof, yeah, that'll work just fine. You can set the inverter right next to the array because they didn't actually say at the array. They said like within 1 foot. So that was all fine. But that didn't work in residential. So then another company came up with the idea saying, how about instead of having one big inverter, why don't we make a bunch of little micro inverters and we'll attach one to each of the panels. And then when it loses sight of the grid, it's just going to shut off automatically at the array. And we'll meet that rapid shutdown provision. Plus, we can put the MPPT in there, so every panel is going to operate independently of every other panel. Problem was, at the time, these little microinverters cost about $200. So if you had 40 panels up on your roof, all of a sudden 40 times 200 is some serious cash. So you're paying $8,000 for inverter, and you could have bought that string inverter for say 2,000. So this added a lot of cost. So then Solar Edge came along and said, oh, you know what we could do is we could put all of the electronic device, the rapid shutdown, the anti-islanding, the automatic, the MPPT, everything that you've got in a microinverter, we can put it in an electronic device except for the inverter. We'll just keep the inverter down in the basement, but we'll put all these other electronics up here. So that became known as power optimizers. And those solved a lot of the problems, and you could make those for like $50. So it was an economic decision. So what ended up happening is in the residential marketplace in the US, microinverters and power optimizers soon came to dominate the whole world of residential solar. And it was solely because we needed to shut off the power at the array when the first responders come to deal with an emergency. So now optimizers and microinverters represent about 90% of the residential market. But this was a response to a regulation that no one knew how to respond to. Now, a couple of things have changed recently, which is the meters in the 2023 code. The old meters just sort of look like a box with a meter, right? And they just acted like a fuse, and you have that little tamper resistant clip there. So they'd come and just break that off and pull the meter out. That's what first responders would do. But in 2023, they said, we don't want there just to be a meter, because one of the downsides of pulling that meter when the power is on, it's like pulling a fuse under load. It'll throw out a pretty good arc, and scare the bejeebies out of those first responders. You pull that thing out and all of a sudden there's a flash and a pop, and they're going to freak out. So they didn't like that. So now they're saying, okay, we want there to be an emergency disconnect right here at the meter. And typically now you're going to have a couple other double pole breakers. So it's almost like a mini circuit breaker box under your meter. So any new installations now have to have something that looks like this, where there's going to be this emergency disconnect at the meter. It's going to be closed, but now when the first responders come, they're just going to open the door and flip the switch to off. So now they're just going to disconnect you from the array just by flipping a double pole breaker, just like the main in your circuit breaker box. So that's good. It's on the side of the house. Well, now if I want to hook my solar array in, let's say I've got microinverters, rather than going and drilling holes back and forth through my roof. Well, if I've got microinverters up here, they're already generating AC, so I don't need a DC disconnect. So you could come out, you could go in the attic, but let's say you just come across the roof, you come down. Well, the first thing you're going to go to is Enphase has a combiner box. Then you're going to go to an AC disconnect. And then you're going to go to your meter, and you can just connect right into that double pole breaker right here in that meter. And that's your whole installation. You no longer have to even drill any holes in your building. You don't have to go in. And one of the big reasons for that, and why that's a real advantage, is if you've ever looked at a circuit breaker box, they're usually chock-a-block full. They might have been installed in the 1970s. It looks like a squirrel's nest. There's just wires everywhere. Nothing's labeled properly. And what we run into a lot with solar installations is you got to put in a new circuit breaker box. There's no space to connect. So, and that's going to be a $2,000 to $10,000 job, depending on where you live. It's going to be at least $2,000. So if you can just hook in here, you've just eliminated $2,000 worth of repairs, worth of upgrade. Now, one thing that a lot of people lose sight of, this bus bar here connects into the main. So inside your basement or wherever your main service panel is, if you're upgrading and putting this new emergency disconnect switch in at your meter, and that's something your electrician is going to have to do, because they're going to have to turn off the power. They're going to have to put in the new box. It's not a big job, but it's a job that I don't want to do as a homeowner or a solar installer. All right. Well, if you ever looked inside your circuit breaker panel, oftentimes there's going to be a neutral bus bar over here, and there's going to be a ground bus bar over here, and then a whole bunch of circuit breakers in the middle, right? And then your main breaker might be up here at the top. It's going to look something like that. All right, so the neutral, the white wire, and the grounding wires are bonded together in this main breaker. But what happens, because there is a jumper or some sort of bond between them, they're effectively, you could put your white wires and your bare copper wires, you could intersperse them in these bus bars. And oftentimes, and you should look in your circuit breaker panel and just see if they're all mixed together, because that's pretty common. Um, that can only happen in the main disconnect box. So this is your main panel. So that's okay. That all works. That all meets code. But as soon as you put this in, this is now your main disconnect. And this, your main panel, is now considered a subpanel. And no longer can those two be mixed or even bonded together. So in here, your neutral and your ground are going to be bonded together, but not here. So you'd have to get an electrician to come in or do it yourself, I guess, if you're good at that. Um, Turn this off and then separate out all of those wires. So all the white wires are going to one bus bar, all the copper wires are going to another. And if there is a bonding jumper, or often in one of the bus bars, there's going to be a green screw, and that green screw goes down and it connects this to the case, and that's how these two are bonded together. So just something that you don't want to forget is if you put in this emergency disconnect, you might have to deal with the ground issue in your main service panel. So that's not so much solar, but that's electrical issues. Okay. Are we clear so far?
I am. Can I ask a quick question? I, I guess nowadays, all the inverters are the minis, unless you're going to switch from AC to DC to AC. Pretty much, that's if you're going to go to a battery there somewhere, you could have to convert it twice. Is that the only time you'll ever see a bigger inverter?
No, you'll see bigger inverters. Well, like I said, Solar Edge has a DC inverter. So that's it's just a fixed voltage inverter. So the optimizers are generating DC electricity. If you've got a ground mounted system or commercial system or a utility scale system, they're all going to be using string inverters.
Okay.
It's just more economical, more efficient. You remember in chapter 3, we talk about DC coupled systems and AC coupled
Mhm.
systems. Well, one of the advantages, let's say I've got an array here, it's going to be generating DC electricity. So if I come out of there and go into a DC disconnect, and then from there I'm going to my inverter, and if I've got batteries here and I connect into my inverter there as well, and then I go from here, I go to my AC disconnect, and then I go to my loads at a double pole breaker in your circuit breaker box out to the meter. All right, there's a certain amount of efficiency with all of this because DC is going in here. If it needs to charge the batteries, it doesn't go through any conversion. It just goes straight DC to the battery. Then from the battery or from the array, they can be converted to AC and go to the loads. So there's only the one inversion, the one transformation between DC and AC,
Mhm.
and that's when it leaves to go to the loads. But between the solar array and the batteries, everything is happening DC. So that has an economy because every time you go from a DC to AC transition, you're going to lose some power. It used to be you'd lose as much as 10%. Now it's down to 1 or 2%. So it's not as big a deal. But if I have say a microinverter system, and I've got all my little microinverters up here, and they're already now generating AC electricity coming out of here, well, it's going to go, for simplicity's sake, just to an AC disconnect.
Mhm.
Actually, I should put in
They turn off. Yeah.
the combiner box because
Combiner
we're going to
box, sure.
do this. So let's say this is my combiner box. So I'm coming in here, then I'm going to go to an AC, and then from there I'm going to go to my service panel. All right. and that's going to go out to the meter. So this is a very simple N-phase type system combiner. Now, if I want to put in batteries here, well, it's AC electricity. So it's got to go into a conversion from AC to DC. And then coming back out, it's got to go from DC to AC and then go back out here. So any power coming from your battery has now gone through three different conversions. It went from DC to AC, then from AC to DC, and then from DC to AC before it ever got to the load.
Okay.
Now, an N phase, and this is one reason why we have proprietary batteries for these systems, is N phase inside that battery pack has a rectifier, which converts it from AC to DC, and it has microinverters built into it that convert it from DC to AC. So, and the battery management system and all of that. The other issue is that all of these devices now have communication systems. So this combiner box has a communication system, your battery bank has a communication system, and so they're all communicating with each other. And so in order to make that communication happen, you've got to use proprietary equipment. So if I'm using N-phase microinverters, I've got to have an N-phase combiner box, I've got to have an N-phase battery bank. And the other thing that N-phase now has is they have a meter collar. And this is where the islanding, this is where they disconnect from the grid. So, and it has a communication system. So all of these things are communicating to each other. So what it's doing is, let's say that the grid goes down, there's a power outage, and you want to use the battery storage. Well, in the meter collar, it's now going to disconnect from the grid. It's going to isolate your whole system from the grid in the collar. And it's going to tell the system now it's working in standalone mode. So the panels are still going to work, the battery's still going to work, but you're no longer have any possibility of backfeeding to the grid. So all of these things are communicating with each other. Then as soon as the grid is reestablished, it's going to reconnect, and then you're going to go into grid tied mode. So you might have power that comes in to recharge your batteries, for example. It really depends on how you set them up. So these become very proprietary. But I would say only about half of the residential systems use this microinverter system. And another 40% are using Solar Edge, which has an inverter, which is a DC coupled system. And then the other 10% are using other things, probably DC coupled. Like Generac has its own system that works well with generators. Tesla, they have the Tesla Powerwall. They've got Tesla inverters now. So there are other products that are out there competing, but for the most part, they're going to be DC coupled systems.
So if you're building an array freestanding, not on a house, would it be cheaper to get it without the microconverters and keep it in DC until you get your battery charged and then run it into the AC converter?
It might.
Yeah.
It depends. It depends on how you want to do it. The microinverters are a bit more expensive. But I'll tell you, when we did it here at the building where I'm at, we put in microinverters, even though it's a carport, it's freestanding out there in the yard. So we technically didn't have any rapid shutdown issues, but the microinverters are very robust. They're guaranteed for 25 years. So I feel like personally, they're higher quality. They're going to last longer. Over the life of the system, they're probably going to be comparable, maybe even a little cheaper than the other ones. The microinverters are guaranteed for 25 years, where one of those string inverter systems only guaranteed for like 10 years. So you're going to have two of those over that lifespan. Now we could question whether we're going to last 25 years or whatever, but that's so I liked working with microinverters with Enphase, so that's the system we install.
Okay.
So it's just going to be a personal preference. But I know a lot of installers who only work with SolarEdge. I know a lot of them who only do Tesla. It's almost like you get into your comfort zone, and if you've got a crew that knows how to install only one product, that's the product you're going to install.
That's what you're going to do.
Yeah. So, all right. So that's turn that off. So that's those are a couple of items: rapid shutdown, the IV curve, the MPPT. Those are some big deals. There's a couple of concepts in chapter 4 that we want to worry about, which is remember I said that there are 3 equations that you have to, oops, I don't want that. I want the whiteboard again. 3 equations that you want to memorize. Okay, the first one is the power equation, which is watts equals amps times volts. So that's the power equation. The second one is Ohm's law, which is volts equals amps times resistance, or Ver. I always just think of it as Ver. So this is known as Ohm's law. And really, on these 2, the only thing from a practical standpoint you need to know is that there's a relationship between these 3 variables. And if you know 2 of them, you can figure out the third one. If you don't know 2 of them, you're kind of lost in the dark. But you'll be asked to do this, certainly on the test, but also in the field. The watts equals amps times volts, very, very helpful. It's a surprisingly easy equation, but it's one that you find yourself going back to a lot. Ohm's law is less, you can think about like in the water analogy, if watts is the amount of water flowing through the pipe, amps is the size of the pipe, and volts is the water pressure. So the higher the pressure, the more water is going to come out. The bigger the pipe, the more water is going to come out. But it's a relationship. How much water is flowing is a relationship between the size of the pipe and the pressure. If we extend that to Ohm's law, volts is, say, the water pressure. Amps is the size of the pipe, but resistance is the friction that the water feels on the side of the pipe as it flows through. So it's going to reduce pressure over distance. It's not going to reduce the size of the pipe. It's going to reduce the water pressure the further it goes, or the more rough that surface is. So the greater the resistance, the less the volts. The greater the greater the length of distance, the less the volts. And that's all because of resistance. It's all because of the friction of the water flowing through the pipe. So the third equation that we need to know is the voltage drop equation. How much loss of voltage are you going to be experiencing? And it's just Ohm's law, voltage drop equals amps times resistance times twice the distance divided by 1,000 feet. Well, it's Ohm's law adjusted for distance. So why do we do this? Why is it twice the distance? Well, if I've got a connector here, let's say it's a junction box, and I'm going to my DC disconnect, and it's 290 feet, it's actually a circuit there and back. The electron is flowing twice the distance. So the resistance is affecting the entire circuit.
Mm-hmm.
That's why it's twice the distance. Why are we getting 1,000 feet? It's because when we look up a number in the NEC, and I think it's the resistance numbers are, I forget which page. I thought it was page 88, but that might be a previous edition. Yeah, it's page 92. So resistance is given to you in ohms per 1,000 feet. So now I need to know what portion of 1,000 feet are we talking about. So when we look up in the table, and if you look at number 10 stranded wire, it's 1.24 ohms. So resistance is 1.24 ohms per 1,000 feet, how many thousand feet? Well, we just said this was 290 times 2 is going to be 580 divided by 1,000 is going to be 0.58. What's the amps? Well, that's going to be the amps of the circuit. We get that off of the solar panel, right? The amps of a string are the amps of a single panel. So if I look at that solar panel and the IMP or is say 9.8 amps,
Mhm.
then my voltage drop is going to equal 9.8 times 1.24
Mhm.
times 0.58. And if we do the math here, and we take that and we say 9.8 times 1.24 times
Well,
0.58, I get 7.04 volts. 7.04 volts. So that's the voltage drop. So when I leave here, whatever I started at, I'm going to be 7 volts less when I get to the DC disconnect. So the question is that acceptable? Well, if it's a 600 volt system, if I've managed to design it up to the maximum, well, 7 divided by 600 is only going to be a little over 1% of lost power, right? Because 6 over 600 would be 1%.
right. I guess.
So, and we try and keep our voltage drop to around 2%, certainly less than 5%. So this is acceptable if it's 600 volts. But what if it's a 12 volt system? Well, if it's a 12 volt system, I just lost more than half of all my power because it's going to get to the destination at 5 volts. So my whole system just I mean, I just wasted half of it. And this is one of the reasons why we use AC electricity today, because back in the day when there was a battle between Tesla and Edison as to who would control, when they tried to get power from Niagara Falls to Buffalo, New York, the DC system had to have regeneration stations like every 5 miles in order to get the power back up because it was losing due to voltage drop.
Mhm.
But AC could use transformers to increase the voltage at the beginning. And by the time it got to the destination, the voltage drop was kind of immaterial. And we see this in our current power grid, where if we've got a power station here, with all the smokestacks and everything, and the high power lines that go across the country,
Mhm.
well, oftentimes these are going to be operating at 700,000 volts. And then it comes in to one of these fenced in place with all the transformers that all the crackheads climb over the fence and try and get the wire and everything.
Mhm.
So these substations. Well, in the substation, when it's now going out to the neighborhoods on the smaller poles, it's gonna step down the voltage to about 7,000 volts. So all those poles that are going through your neighborhood are going to be operating at about 7,000 volts. And then you get to that transformer that's on the pole near your house, that can that's up on the pole, and it's going to feed it into your house at 240 volts. And all of this is just to avoid the impact of resistance. So, because this might travel for 100 miles, and if it's losing, I don't know, let's say 10 volts for every mile, well, it just lost 1,000 volts, but 1,000 out of 700,000 is not that material. And then these distances are shorter. So by the time you can actually go from Illinois to New York City and only lose about 10% of the voltage that you started out at. So wind turbines in Iowa can literally power New York City without that much loss. So when they always say the wind doesn't always blow and the sun doesn't always shine, I always say, yes, it does somewhere, you know. And when you start adding in batteries, then it really doesn't matter when the wind is blowing or the sun is shining, which is one reason why our grid is very rapidly transforming to renewables.
Mhm.
Because when you look at straight pricing, the options today, when you're putting in a grid or when you're putting in power on the grid, there are really only four options. There's natural gas, there's batteries, there's solar, and there's wind. And you wouldn't necessarily think of batteries as a generating source, but if you really think about it, coal, oil, and natural gas are nothing more than stored energy. It just was stored over millions of years. So a battery is similar to fossil fuels, except that the storage takes place over a much shorter time period. So it's another energy source. Um, well, for the first time this year, solar plus batteries is cheaper than natural gas. So that's why 100% of all of the power being added to the grid this year is going to be wind, solar, and batteries. And fossil fuels will have a net zero growth on the American grid, which you wouldn't think of because of all the noise we hear from the politicians and all of
Yes,
that.
especially here in West Virginia.
Oh yeah, well you guys, coal died about 10 years ago. It's just that nobody let anybody except
Well,
Joe Manchin know that.
well, if I might digress, I think that it's a drives me nuts because I think the future of coal, if there is one, is integrated with these systems with batteries so they can burn when they're cheap and when we need them and not burn the rest of the time rather than this all in philosophy because it makes us look like we just had this big conference about these data centers and how they want renewables as part of the system. And that makes us unattractive here because we're all in on coal. So I just think these very short-sighted politicians here are really hurting our long-term prospects for our natural resources. But that's just me. So
Yeah, I think coal has a real problem because it's really only used in two industries, electric generation and working with metal, like
right,
aluminum and iron. Natural gas is a lot cheaper and more efficient in both of those industries and not as polluting. So the coal industry, well, first off, it moved away from West Virginia and went up to North and South Dakota a while ago. So the
right.
power basin basically replaced West Virginia. And the reason is it was cheaper to get it out of the ground than in West Virginia because it's mostly strip mining, and that's just a lot cheaper than digging deep into the ground. Coal currently costs about three times as much as wind and solar. So when you're putting in electricity, you don't necessarily care what power source you're using. You just want electricity and you want it as cheap as you can get it. Nuclear costs about 10 times as much. So why on earth would you build nuclear? And so really, for the last 10 years or so, natural gas was the only competitive fossil fuel when it comes to generating electricity. I personally believe that the natural gas industry will do just fine. Everybody will look at them though and go, "Can you believe we used to burn this stuff just to make steam?" Because it's too valuable. It's too valuable in plastics. It's too valuable in medication and fertilizer and all of these other industries to just burn it. It's like taking mahogany and using it as firewood. Why would you do that? You have a more valuable commodity. So wind and solar, well, wind is only helpful if you've got wind. So a lot of these, like if you go over to eastern West Virginia, there's a lot of wind over there near Maryland. Um, but in a lot of places, it's just not available at any scale. But solar is available everywhere. So solar is really the near term solution. Somebody may come up with something with fusion or some other thing that we've never heard of, but that's 20, 30 years in the future. And the question is, it's not if we can do a thing, it's like, can we do a thing at a price point that's competitive? And that's where nuclear falls down, and that's where hydrogen falls down, and fusion, all of these other things. Yeah, we can do them, but why would we pay 20, 30, 10 times more than the alternative? It's like Joe Biden always used to say, don't compare me to the almighty, compare me to the alternative. Well, so the coal industry, regardless of what West Virginia wants, is dead.
Yeah.
There's no resurrecting it. There's no use of this thing. Time to get out.
Well,
Natural.
and we had the and so I worked for the legislature. I've been up here for 30 some years. I've worked for the Democrats, but we had our opportunity when we discovered Marcellus formation here. That was the transition moment for us. We should have been all in on that and moving our entire energy system over to natural gas. That was that's the future for our small state. And they're just, Colby just hasn't have us by the throat in the friggin' legislature. It's unbelievable.
Yeah,
We
it's
have,
funny. I think about when I was in high school here in Southern Ohio, and the worst thing in the world was to get stuck at a railroad crossing when the coal train was going past. And you sit there for 20 minutes as these cars just went by and by and by. And today, every single coal mine in Southern Ohio is closed. I mean, there is no coal industry in this region, and the same thing is happening throughout West Virginia.
yeah.
You know,
Well, and
all
that's right. And I'm super excited. And one thing that Biden did for us, I'm really grateful, is on the Northern Panhandle, converting the old Weirton Steel into a battery manufacturing industrial battery. We should be all in on that stuff. And I'm glad that we got one manufacturing facility in the state that's looking to the future. So, uh, but
well,
that's these industrial sized batteries are going to be huge when they get up and really impacting the grid.
yeah,
Uh,
for the next 10 years or so, batteries is really where the energy market is at. Solar is going to be growing, but batteries are going to be growing
mm,
exponentially.
yeah.
So we're already hampered a bit in the battery market by tariffs and our obsession with the Chinese. It's interesting on our Solar Noon Tuesday, we'll talk about this and we'll talk about the pricing of US batteries. And a Tesla Powerwall costs about $8,000 for a 13 kilowatt hour battery. But some of the guys in Europe or Trinidad and Tobago or Africa who are on the call, they say we can buy that for $1,000.
Mhm.
So why are you guys paying 8 times as much for the same storage capacity? And it really is government policy. There's some regulatory, there are certain hoops they have to jump through in order to access the American market, which are not all bad, um, but putting 100% tariffs on and other requirements that add 2, 3, 400% to the cost. My attitude with Chinese panels, solar panels, was always if the Chinese want to subsidize me putting solar on my roof, I say we should let them. It's like we don't have a domestic market of any sort. Uh, we're not really going to develop one. Most of the companies that have moved into the US because of the preferential treatment for American panels are Chinese owned, so we're just basically moving the place of the factory. All the money still goes back to China. So yeah, we should, we're trying to compete in rotary telephones, how about if we own the next generation? So
So
anyway, that's my soap opera. That's why I've
I'm
never
with you, Jay.
legislature. They wouldn't let
I'm,
me.
yeah. I'm 100% with you on all this. And I got so upset. I've been thinking about solar my whole adult life, just not been in a position to do it. And I was so enraged when the big bastard bill took away the tax credit. But I just said, I'm not going to let that stop me. I really want to do this. And I still think it's a great deal, even if we lost the tax credit. So I'm jumping in. So
Yep.
should have
Well,
done
and
a
I
thing.
think you're going to find, I mean, my sense is the next guy, we're going to see a dramatic shift, a ricochet away. The next guy who gets elected will be the anti-Trump, it'll be
Mhm.
everything about him will be the opposite. And I think the lesson that was learned under the Biden administration was they had good intentions, but they were so slow to implement all of
Mhm.
these things. You come up with money and then it takes you 3 years to get the money out the door. That's crazy. So I think they're going to probably it's going to be a lot of incentives coming out quickly. because I suspect there's going to be a lot to repair.
Yeah,
So
I agree.
anyway, so chapter 4, the electrical, I think we've pretty much jumped through that.
Mhm.
Chapter 5, the whole goal of chapter 5 is to sort of walk you through from the solar panels all the way through the system to the end load and talk about what are all the different pieces of equipment you're going to meet along the way, and why would you what are the capabilities of each of these pieces of equipment, and why do you pick one over the other. So that's really the structure there of chapter 5. We talk a lot about the different options of inverters. There's a lot of information there. I think the one thing I would like to highlight from this chapter, there's a lot of information in there. We don't really have time to do it with this call, but if you'll remind me to do it on the next call, is sizing the wire. You know, how do you go through and size the wire appropriately within your system? So we'll hold that for next week. But and next week, I think we have trying to see what the schedule is looking like. Yeah, next week we finish up chapter 5. So that's good. I can do the wire sizing then and conducting a site survey. I think conducting a site survey um, is is probably the most intuitive chapter. You know, some of this stuff is you're not born knowing about electricity, you're not born understanding configurations of systems, but you can sort of intuitively know that when you're going to install a system on your home, what do you need to worry about? Where are you going to put it? How are you going to orient it? You know, so it's very practical in nature. So when you get into chapter 6, I think most students don't struggle with that.
That's good to know.
Yeah, it's very intuitive. Then chapter 7, we start getting into some of the math. That's when people's brains start to hurt. So so we're kind of this next week will be sort of the last of the easy easy chapters, and then you're going to get into the ones that are going to be a little bit more taxing. So
Okay, I thought that this chapter 5 was pretty challenging trying to get all that because it's all brand new to me. I'm just trying to learn everything, and I don't have electrical background, but I just keep rereading it, and it does make sense. It's if you keep looking at it, it's intuitive. It's in a certain way, it makes sense.
yeah.
Like, you know, I wanted to ask you about how we figure the volts versus amps, whether you run the parallel or you mix them, but we'll talk about that. I'll come up next time.
Yeah,
So,
we'll talk about that because that really gets to the heart of wire sizing, and voltage drop is a big issue. You want to push the voltage as high as possible because it minimizes the cost of your system. So we're limited with the voltage that we can operate under. In a residential system, that limitation is 600 volts.
mhm.
In a commercial system, that limitation is, I always get the European mixed up, but I think it's 1,000 volts. It might be 1,500. But yeah, you would think that 600 volts or 1,500 volts are more dangerous, but they're really not. The You'll die if you get electrocuted by 120 volts. You'll die if you get electrocuted by 1,000 volts. You know, it's mostly the amps that'll kill you. That's the main thing. So the higher the amps, the more dangerous it is. But that said, I mean, it's a combination. They'll both kill you. I always think about that scene in, did you ever watch Butch Cassidy and the Sundance Kid?
Oh yeah, the fall will kill you.
Yeah, it's the fall that's going to kill you. You don't worry about drowning. So yeah, but the higher the voltage, the smaller the wires can be, the less amps are going to be there, the fewer switches, the fewer disconnects, the fewer breakers. So you save a lot of money by pushing your voltage up as high as possible, and you lose less in voltage drop. So that's one of the reasons when you're configuring, try and push yourself up as close to that limit as possible. Um, and and then, you know, obviously you can't go above the limit, but then the amps are going to be the other issue. So yeah, we'll touch on that in chapter 5
Okay.
next week.
All right. I look forward to it.
All right. Take care.
All right,
Bye-bye.
Jay. Take care. Have a good week.
You too.